This is AQA A-Level Chemistry. It's a Year 13 topic, Aromatic Chemistry, and this is part 1 of 2 of Aromatic Chemistry. In this video, we are going to take a look at Kekule's structure of benzene, and we're also then going to look at the evidence that disproved that Kekule's structure was correct. A really important component of learning, and it is very commonly seen in the exam. As always, I am going to recommend that you pause the video as you go, have a go at the different activities, and then check for yourself how confident you are with the knowledge that you need to know. So we're going to start off actually with a little bit of a review of some Year 12 mechanistic work. So if you can take a look at this mechanism, try to work out how many errors there are. So I'm going to start off by redrawing it below, and so far I have got my two compounds correct, my C2H4 and my HBr, but we're already spotting some errors. First of all, we've got the arrow going from the carbon to the H. Now, curly arrow will always represent the movement of electrons from electron rich to electron deficient. There are two errors here that we're spotting. One, the hydrogen should actually be delta positive. This is a permanent dipole and bromine is more electronegative. But secondly, if we're having electrons flowing from a higher electron density, in this case, they actually go from the double bond. Now, when they go from the double bond, that then means that the C has formed a bond with the H, which means the HBr bond can no longer exist. So we need to show the breaking of that HBr bond. We've got the curly arrow going from the bond to the Br. But once again, there is an error in the example that we've been given. Because the two dots have been put on either side of the bond, you're essentially saying there that one electron is moving. So we don't include those in the mechanism. Now, from there, we go on to produce our intermediate, and we also have a Br minus ion. So there's an error here that it's Br minus. They have not included the charge, but they've also missed out the fact that this is a carbocation. They've not put the charge on the C. And then from there, they've done an arrow, but they've put it in the wrong direction. Again, electron rich to electron deficient. From here, it's the electron-rich pair of electrons, my negative to my positive carbocation. From there, we have drawn the final compound successfully, but we have not named it correctly. There's actually two carbons in the chain, so calling it bromomethane would be an error. It's actually bromoethane. I think what's important to point out here is that the mechanism drawn at face value looks like it could be very, very good, but it is filled with fundamental errors. And this actually highlights perhaps somebody who has tried to learn a mechanism as an image, as a snapshot. And when there are so many mechanisms to learn, it's far more important that you understand the principles and the reasoning why. Mechanisms are about why a reaction happens, and you need to understand each step of the process. With that in mind, have a go at drawing the mechanism for the reaction between ethene and bromine. So start off by drawing the two of them out. I have got my first arrow going from the electron-rich double bond to my bromine, and it's actually a delta positive bromine for reasons that we will come to in a moment. That then means that the Br-Br bond will break, so we have our arrow going from the bond to the other Br. That takes us to our intermediate structure, our carbocation structure, which we can see here, and I've got my Br minus with my final arrow going from the lone pair, not from anywhere else on the Br minus, but from the lone pair to the positive carbon. So why is the bromine acting as an electrophile here? Have a think about it, and we'll talk about the answer in a second. First thing to look at is that we've got an electron-rich double bond. And you'll see that I've drawn the Br-Br in a particular way. It is useful to draw it that way, because then you can actually visualize those electrons repelling the electrons in the Br2 molecule. And when they repel them, it pushes them away. So this bromine becomes more delta negative, it becomes more electron rich. This bromine becomes electron deficient, delta positive. That means a dipole has been induced in the Br2. And that then means that the electron-rich double bond can attack the delta-positive bromine, and the arrow there represents it. So we're going to move on once again. Let's take a look at the reaction between cyclohexene and bromine. Have a go at the mechanism, think about what you would observe. Well, the mechanism follows exactly the same pattern, even though it looks a little different. I've got my double bond attacking the delta positive bromine, and I've then got the electrons being shifted, and we can see the movement of electrons with the second arrow going from the bond to the Br. That leaves me with my carbocation structure. The double bond has gone, my Br has been attached, and I have a second Br, I've got a Br minus ion now, and that will attack the positive carbon. Once again, you'll see it's going from the lone pair. So what would you observe in this reaction? What would you actually see? Well, this takes us back to our knowledge of GCSE chemistry. The brown bromine water would be decolorized, or it would turn colorless. Very important words to learn. They do not go clear. Colorless or decolorized are what you must say. So the remainder of this video is going to be focused on the structure of benzene. It is a very important story, the history of benzene. It took a long time to get to the structure. Initially, one of the big problems was working out how 6 carbons could only have 6 hydrogens connected to it. And one of the first major steps in terms of getting to the structure was the understanding that it was a cyclic structure, a ring structure. Now, in year 12, you have learnt about cyclic alkanes, and specifically that they are a functional group isomer of another homologous series. What are they functional group isomers of? And cyclic alkanes are functional group isomers of alkenes. Let's take a look at an example. If I take but2-ene and cyclobutane, they both have the molecular formula C4H8. Now, that definitely fits with the general formula of an alkene, we know that. But it also then means that if we follow through the definition of functional group isomer, same molecular formula, but different functional groups, then we can see that they're functional group isomers of one another. Now, Kekule was somebody who did a lot of work on the benzene structure. He had dreams of snakes eating tails, which led him to the idea it was cyclic, and he came up with the structure that we can see on the left. What would you call this structure based on the rules that you have learned? Well, there are 6, so it's hexa. It's a cyclic compound, so it's cyclo. There are alkenes, so it's going to end in ene. And there are 3 of those enes, so that makes it triene. But we need to number them. We need to see or say where they are. So we can see the first one starts on the first carbon, second on the third, third on the fifth, cyclohexa, 1, 3, 5, triene. Now, Kekule did a lot of hard work, but there were huge amounts of evidence that disputed his structure, and we're going to take a look at each of them in turn. In the first instance, I want you to consider, if this were the structure, how many different isomers would there be of dibromobenzene? Now, I want you to name it in the way that we just did. So this is cyclohexa 135 triene. What would you call each of the 4 structural isomers? Well, I've put the BRs on so we can see them. Some of these might look quite similar, but note carefully, in this one, they're 2 apart. In this one, they're 3 apart. In number 1 and number 4, they're 1 apart, but here they span a double bond, and here they span a single bond. So let's get to the naming. Now, alkenes, or the ene, has a higher priority than the haloalkane. So the numbers will be based on giving us the lowest possible numbers for the alkenes. So the first one is 1,2-dibromo, cyclohexa 135 triene. The second one would be 1,3-dibromo, cyclohexa 135 triene. The third would be 1,4-dibromo-cyclohexane-1,3,5-triene. The fourth one is potentially a little bit more difficult. Remember, we have got to have the double bonds at the lowest possible position. That means that we have to start numbering here or here and work our way round. It actually means that on this one we have 1,6-dibromo-cyclohexane-1,3,5-triene. But benzene doesn't actually look like this. Benzene is commonly shown as a circle in the middle, and we'll talk more about what that means a little later on. But if that's the case, how many different isomers here would there be? Well, there's one. There's another one. That's definitely different. They're 2 apart. Here's another one. They're now 3 apart. We haven't got any others, because if I went to 1 and 4, that's a mirror image of the one we have here. So we have got 1,2-dibromobenzene, 1,3-dibromobenzene, and 1,4-dibromobenzene. There are only 3 isomers. According to Kekule's structure, there would be 4, and therefore it counts as one piece of evidence to dispute Kekule's structure. So let's look at evidence part 2. The bond lengths, I've actually put these in for you. They are available for you to go and find if you need to. 0.154 nanometers for a carbon-carbon single bond. A carbon-carbon double bond is only 0.134 nanometers. It's shorter. That makes sense because you've got 2 pairs of electrons pulling in those positive nuclei, pulling them in tighter, and it will be slightly shorter. Now, if you actually look at a benzene ring and find the bond length, you see that the bond length is actually 0.14 nanometers. First thing to notice there is that the carbon-carbon bond length is between a single and a double. It's almost a hybrid of the two. So it's not single bonds, it's not double bonds. If we were to follow Kekule's structure, they would not all be the same length. This is an exaggerated version, but here the double bonds are much shorter than the single bonds, and it is actually a regular hexagon. So that is not the case. Kekule did not give up. He took that theory, he adapted it. What he then suggested was that there were actually resonance structures where the double and single bonds could swap places very, very quickly, which led to the bond length averaging out. However, there was still more evidence to come. And we're going to take a look at part 3. What would you expect to see if the reagents above, even in that hybrid structure where they're resonating from one to the other, if I added bromine, what would you expect to see? You would expect to see the brown bromine turn colourless. You'd expect it to be decolorised. We're back to those key words again that were mentioned earlier in the video. However, if you've done some research into benzene and bromine, what you will know is there is actually no visible change. Benzene does not decolorise bromine water. Now that tells us there are not these double bonds that Kekule had suggested. So now let's move on to evidence part 4. And we've got here the hydrogenation of cyclohexene and the hydrogenation of cyclohexa-1,3,5-triene. We're told at the top one, the enthalpy change is 120 kilojoules per mole. What would you therefore expect the bottom one to be? Remember, this is Kekule's proposed structure for benzene. You'd expect it to be 360 kilojoules per mole. Now, what we then need to do is compare that to the actual enthalpy of hydrogenation of benzene. So I've put the 360 up there again, and I will tell you that benzene has an enthalpy of hydrogenation of not 360 kilojoules per mole, but just 208 kilojoules per mole. And what that actually tells us is that benzene is much more stable than cyclohexa-1,3,5-triene, which is what Kekule had initially proposed. So we're going to finish off by actually looking at the structure of benzene. As we've already touched on earlier within this video, it is a cyclic compound, 6 carbons. It's generally drawn skeletally. Each of these bonds coming off would have an H coming off it. And the reason I've put those on is so you can see there are 3 bonds coming from the carbon, which strikes you as unusual. And it's also to help you to see the bond angles, because in each of these cases, the bond angle is 120 degrees, something that you'll be familiar with from the bonding topic for trigonal planar structures. About each carbon on the benzene, there is a trigonal planar structure. The actual complexities of the shape are worth looking at. So you can see here that we have got our delocalized ring of electrons. We start off with the electrons pointing up and down that we can see in the top one. Each carbon, because it's only forming 3 bonds, has a 4th electron that is therefore not being used to bond. They come together to make the delocalized ring of electrons. Now, they actually add a lot of stability to benzene, and that helps to explain the increased stability in comparison to cyclohexyl-1,3,5-triene or Kekule's original proposed structure. So in the next video, we're going to take a look at the mechanisms that you need to learn regarding benzene and some of the other reactions. But that takes us to the end of this video. Thank you for listening, and goodbye.